It's a pleasure to have as guest for our complex analysis seminar, Gian Maria Dall'Ara from University of Birmingham, plus Indam plus Normality Pisa, on a theme in analysis on general smooth pseudoconvex domains. Okay, Gian Maria.
Okay, thank you very much. It's a real pleasure to be able to present some of my recent research in this novel format. For me, it's the first time to speak to a screen, so let's see. Stop me as always if you have questions. Okay, this is what I'm going to talk about is mostly joint work with Samuele Mongodi of the Politecnico di Milano. And let me begin, since the title was admittedly quite vague. It's, I guess, the kind of title that would be good to accompany with an abstract. So I'll try to clarify immediately what I'm going to talk about. So what we investigated are two fundamental invariants associated to general smooth pseudoconvex domains. And these are the Diderich-Fornès index, introduced by Diderich and Fornès in 1977, and the so-called D'Angelo class. Okay, this is not a very standard name in the sense that this is a lesser known object, but okay. In some papers, it's already called D'Angelo class, and we follow this nomenclature. And this was, of course, introduced by D'Angelo, but mostly effectively used for the first time, I guess, by Boas and Straube in a 1993 paper. Let me just to start with to clarify, to remark that one of the consequences of one of our main results is that in a quite large class of domains for which the Diderich-Fornès index is 1 is identified compared to what was known previously, I guess. I will also try to stress and clarify what is the relation of this condition with the well-known problem of regularity of smooth extension of biolomorphisms between domains in several complex variables. And of course, our work doesn't come in a vacuum. It's very much related to recent work of Bingyan Liu, which is interrelated to work of Krantz and Marco Peloso. And you will see later, I will also cite work of Yume and Adachi, very recent work from 2019 and 2020. Okay, but let me begin with the, okay, here I put as a reminder the fact that when I forget to say that a domain is smooth or bounded, this is always assumed implicitly. So if I forget, always think about a domain as smooth and bounded and in Cn. Most of what I'm going to say works on more general manifolds, certainly on Stein manifolds, and certain results also even on more general manifolds. But I will stick to Cn for simplicity. Okay, let's begin with the basic definitions. I start with a domain defined by a defining function R. As usual, the defining function will be assumed to be to have a non-vanishing gradient on the boundary. The boundary M is, of course, the set of points where the defining function is equal to 0, and the domain is always assumed to be pseudoconvex. Okay, and I will recall in a moment what that means, but I guess most of you know better than me. And the basic object we are going to deal with is the standard CR bundle on M. So since M is a real hypersurface as the boundary of a domain in several complex variables, then it comes equipped with a natural CR structure, which is the CR structure inherited from the ambient complex structure. So of course, this is a complex subbundle of the complexified tangent bundle, which I indicated here to have a real rank, complex rank 2m-1. And the standard CR bundle is usually denoted T10M, is the bundle whose sections are vector fields of type 10 that kill the defining function R. This bundle has, of course, rank n-1. Okay, and the Levi form is a quadratic in Hermitian form, non-negative Hermitian form. In fact, non-negativity is exactly, the definition is exactly equivalent to the notion of pseudoconvexity. of course, this quadratic form lambda, which is defined on two vectors, lambda1 and lambda2 in the CR bundle T10M, is defined as the DD bar R, so the complex section of R evaluated in L1 and L2 bar. And as I said, pseudoconvexity is equivalent to the non-negativity of this quadratic form, so to the condition lambda of L bar greater or equal than 0 for any L in T10M. And in fact, the main protagonist of this talk will be the Levi null distribution. So the focus here is trying not to make much assumptions on the structure of the domain on top of smoothness and pseudoconvexity. And so this brings to the fore the complexity of the Levi null distribution. The quadratic form is non-negative, so at every point we have a subspace consisting of all the vectors that are in the kernel of the form, since the form is non-negative, of course, to be in the kernel, in the sense that lambda L m bar is equal to 0 for any other vector field m, is the same as requiring that lambda L bar is equal to 0. So Nm is a distribution at every point of the boundary of the domain. It is a complex subspace of T10M. And this complex subspace, this is an important thing, may have varying rank, may have dimension that depends in a non-continuous, well, of course, in a non-continuous way in a sense, because it's a integer valued, but it's not constant. Okay, so if you change the point on the boundary, the dimension of the null space of this quadratic form may change. Okay, I hope not to say too many times bundle, but we agreed to call this object the Levi null distribution, because bundles usually in differential geometry are required to have at least locally constant rank. Okay, sometimes it's also convenient to work with the real version of this, of both the CR bundle and the, as I said, the Levi null distribution, which are just the real parts of the corresponding complex bundles. So HM as a real distribution has constant rank 2n-2, so it's codimension 1 in the tangent bundle, and it's actually a vector subbundle because the rank is constant and it depends smoothly on the point. But again, the real Levi null distribution may behave irregularly. In fact, the rank as a function of the point, so the dimension of the fibers of the Levi null distribution, is an upper semi-continuous function of the point. In particular, you can certainly say that the set of weakly pseudoconvex points, that are those points for which there is a non-trivial vector in the kernel of the Levi form, so where the Levi form degenerates, this set of points is closed. And this is, again, one of the key objects in play. You have to imagine this bounded domain, and there is an open set, which is the set of strictly pseudoconvex points, those points for which the null space of the Levi form is trivial and the Levi form is non-degenerate, strictly positive. And there are other points where there is a degeneration. And it's exactly the behavior of this set that is the main of main interest here. So as I said, strongly pseudoconvex domains are a very special class of domains, and they correspond to the case where there are no weakly pseudoconvex points. And of course, the classical example, the simplest and most symmetric example, is the unit ball. In a very special case to be kept in mind is the dimension 2 case. In dimension 2, T10M, which has, as I said, rank n-1, has rank 1. So the Levi null distribution at any point may have either trivial fibers or fibers of rank 1. So the whole information about the Levi null distribution is encoded in the set of weakly pseudoconvex points. But of course, in dimension 3 or higher, the situation is way more complex. But already in dimension 2, W is a very complicated object. Because if you don't assume any other regularity on the domain on top of smoothness, for example, real analyticity would make the geometry somehow easier. The set of weakly pseudoconvex points can be quite arbitrary, compact subset of the boundary. An example that I put in evidence here is the examples of domains that are defined by imaginary part of W equal of phi of Z in two complex variables Z and W, where phi is a smooth function. Pseudoconvexity corresponds just to the condition that this function of Z is subharmonic. And so the set of weakly pseudoconvex points will be, since the Levi form can be identified with the Laplacian of phi in appropriate coordinates, then the set of weakly pseudoconvex points is just the points where the Laplacian vanishes. But the Laplacian of a smooth function is an arbitrary function in two complex variables. At least locally, its zero set can be an arbitrary compact set. So this shows you how weird can the set of weakly pseudoconvex points be. So let's begin to try to orient ourselves in the vast variety of pseudoconvex domains, smooth bounded pseudoconvex domains in Cn. The first class to be kept in mind is the class of D'Angelo finite type domains. Those are the domains for which the boundary has bounded order of contact with possibly singular complex curves. So what this means is that, for example, if you take the domain omega, this is one of the simplest examples one can think of in two complex variables. Mod z1 squared plus mod z2 to the power 4 is less than 1. So compared to the ball, you modify an exponent to 2 to 4, from 2 to 4. Well, this domain, in this domain, the Levi form degenerates at every point of the boundary where z2 is equal to 0. This is, of course, a real circle in the boundary, but at these points, the order of contact of the boundary with complex curves is bounded above by a constant. In this case, the constant is 4. Okay, so finite type means that there is there may be a lot of weakly pseudoconvex points, but in fact, there is a constraint on how flat, Levi flat, can the boundary be, and this is expressed in terms of order of contact with complex curves. A slightly more general notion, in fact, the fact that D'Angelo finite type implies this more general notion called weakly regular is itself a deep theorem of David Catlin, is the class of domains whose boundary admit a stratification of compact sets S0, S1, Sn, as you see here, with the property that points in Sj minus Sj plus 1, okay, so the complement of Sj plus 1 in Sj is locally covered by submanifolds. So any point as a neighborhood, which is with the property that points of Sj minus Sj plus 1 are contained in a submanifold V, that should have the following two properties. The first is that this manifold should have constant CR dimension. This means that the intersection of the tangent bundle of V with the J of TV, J is the complex structure inherited from the ambient space, should have constant rank. And the second key property is that the complexified tangent bundle to V should be transversal to the Levi null distribution. In other words, in real terms, let's say inside the real tangent bundle of M, what you should see is that the real null distribution of the Levi form should be transversal to the maximal complex subspace contained in the tangent space to V. Okay, this is a condition called zero holomorphic dimension, which will appear again later. And as I said, D'Angelo finite type implies weakly regular, but there are, of course, weakly regular domains that are not of D'Angelo finite type. This is a simple example. Elaborations of these examples appear in a paper by Kranz, Leo, and Peloso. In this case, again, there is a simple stratification because essentially the set of weakly pseudoconvex points is the same as in the case of the pseudo-ellipsoid. This is the way the domains mod z1 squared plus mod z2 to the power 4 are less than 1 are called, with, of course, more general exponents possibly. And so the set of weakly pseudoconvex points, is the same, but these points are not of finite type as a consequence of this infinitely flat smooth function. Okay. Other important example, in fact, the key example for us is the class of domains that have the property that they contain a complex variety or complex manifold in the boundary. Let me go back. Both D'Angelo finite type and weakly regular domains have the property that no complex manifold can be contained in the boundary of the domain. So to go outside of this class, we look at domains with the property that their boundary, so omega again, as always, will be a pseudoconvex domain. The boundary is smooth and the boundary is called M. And here remarked again that the real dimension of the boundary is 2n minus 1. So there is certainly, in principle, a lot of room for complex submanifolds of Cn. I'll consider a case of a complex hypersurface X. So X, a complex hypersurface, will be from the real point of view a smooth submanifold of Cn of real dimension 2n minus 2, so of codimension 1 inside the boundary. So this is a very specific situation. So when a domain contains in the boundary a a complex hypersurface, then the following can be observed. So first of all, the submanifold X, the complex hypersurface as an hypersurface in Cn, is Stein. Okay, I'm being a bit sloppy about the precise definition of the boundary of X, so I just want here to convey the structure of the problem. When you have a complex hypersurface inside the boundary, then as a consequence of the Steinness and the Grauert theorem, essentially the tubular neighborhood theorem in several complex variables, on complex manifolds, a neighborhood of the hypersurface in Cn is biolomorphic to a neighborhood of X in X cross C, so Cartesian C. In general, a neighborhood of an hypersurface will be biolomorphic to a neighborhood of the zero section in the normal bundle, but the normal bundle is trivial because the manifold is Stein. Okay. In other words, what this means, is that near X, using coordinates coming from the normal variable WC, as you see here, the boundary can be expressed in the following form. The imaginary part of e to the minus I h of z, where h of z is a smooth real valued function times w, is equal to something that vanishes to second order in the variable w. Where the important thing is the fact that h, the function h, is pluriharmonic. Okay, can be assumed to be, it can be shown to be pluriharmonic. So whenever a complex manifold is contained in the boundary of a smooth domain, of a smooth pseudoconvex domain, this is the key property. Pseudoconvexity forces this phase h, this real valued phase h, to be pluriharmonic. And let me recall you that on Stein manifolds, pluriharmonic functions can be defined cohomology, the rank cohomology classes. In fact, there is an isomorphism, thanks to Steinness, between the space of pluriharmonic functions, real valued functions on X, modulo real part of holomorphic functions, and the first, the rank cohomology group with real coefficients. In other words, you take your phase H, and then you compute the DC of H, which is I d bar minus dH, and this closed form, which is closed as a consequence of the pluriharmonicity of H, defines a cohomology class. And in fact, what I'm saying here is that any possible cohomology class comes from such a representative. And this representative appear naturally as soon as you have a complex hypersurface inside the boundary. Okay, so let me give a picture, not very sophisticated technologically, sorry. I used paper and pen. And what I exemplified here is the case of a boundary containing a Riemann surface with boundary. So you take your favorite Riemann surface with boundary, X. In this case, I took one with 3 components of the boundary and genus 2. And then, as I said, I want to, there will be a pluriharmonic function H, real valued. In this case, is a harmonic function. So on your Riemann surface, you get this harmonic function H. And you are quite free to build them in various ways. An interesting class that I wanted to put here is the class of solutions of a Dirichlet problem with locally constant boundary values. So you solve the Dirichlet problem, which you can in this situation, and you find the harmonic function with the property that on the 2 components here, for example, C1 and C2 takes the values A and constantly A, and on the component C3 it is constantly equal to B. Okay. In this case, you can imagine H as this real valued function. I put this depiction in the form which would be typical for Morse functions. In fact, generically, these functions will be Morse. And since the genus is higher in this situation, you are forced to have also critical points. And if you look at the domain in 2 complex variables with the property that its boundary contains such a Riemann surface, then what you discover is that basically over every point, which is not a critical point, you will find in general some piece of real curve. Okay, here you have to think that locally the boundary is a real hypersurface inside the trivial bundle over X. So you consider X Cartesian C, and then over every point of X there is a full complex plane. And what I depicted here is the intersection of my hypersurface, the boundary of my domain, with this complex plane. and the curve will have a tangent, and here it's clarified how the function h is constructed. It's just the phase that determines the slope of the tangent to this curve, which passes through the origin, of course, because the Riemann surface x is contained in the boundary. And what happens here is that the set of weakly pseudoconvex points in this situation corresponds to all the points with first coordinates z in x and second coordinate 0, plus exceptional points, full circles or more complicated curves in more general situations over the critical points. So this already shows you some complexity of the possible shape of the set of weakly pseudoconvex points in the boundary. In this case, it is a Riemann surface with boundary union a bunch of real circles. Okay, the most famous examples of domains containing complex hypersurfaces with boundary in their boundary are the Dieterich-Fornès swarms. These are well known and correspond in this picture to the case where the Riemann surface is just an annulus. So the simplest case you can imagine, where you can have some non-trivial cohomology class. And the harmonic function is a generator, actually, of the cohomology in terms of the correspondence that I described here. So in this case, the associated cohomology class is imaginary part of the z over z, which is a generator of the real cohomology. So in a sense, this is the simplest non-trivial example of a large class of domains containing Riemann surfaces in the boundary. Okay. Here I tried just to put a map of all just a partial taxonomy of a smooth pseudoconvex domain in several complex variables. The simplest one that one could think of are the strongly pseudoconvex domains. As I said, these are the domains where you have no weakly pseudoconvex points. And then another class is the class of pseudoconvex domains, C omega pseudoconvex domains with real analytic boundary. And both these classes, which are of course none is included in the other, but both are included in the class of D'Angelo finite type domains. In fact, the fact that real analytic pseudoconvex domains are D'Angelo finite type is already a deep result of Dieterich and Fornès. And as I said, D'Angelo finite type implies weakly regular thanks to a result of Catlin. And this whole class of red or slightly pale red domains are all contained in the huge class of domains, not containing any complex varieties in the boundary. So weak regularity implies no complex variety in the boundary. Other examples of independent classes are the convex domains. These are much simpler from many points of view, but still they may admit complex varieties in the boundary. When this happens, as we also heard from Filippo's talk a few weeks ago, in this case, then you have actually affine subspaces in the boundary. And convex domains are special kinds of domains admitting a plurisubarmonic defining function, which of course is a condition implying pseudoconvexity of the domain. And an even more exotic class is this class of generalized Dieterich-Fornès swarms, which in fact admit no plurisubarmonic defining function if the cohomology class that I described in the previous slide is non-trivial, and of course they contain non-trivial complex varieties in the boundary. So here I just put some of the literature involved, which is very rich. So this is the kind of variety of domains one has to deal with. Okay, but let's go to the heart of the talk. What I want to talk about are global invariants for smooth bounded pseudoconvex domains. So as I said, two of them are of special interest for us now, the D'Angelo class and the Dieterich-Fornès index. Okay, what is the D'Angelo class? You start with a smooth pseudoconvex domain in several complex variables, but actually all I'm saying here works for smooth pseudoconvex domains, which may be unbounded and even contained in a more general manifold. So at least what is contained in this slide. And what you do is the following. You choose any theta, which is a real one form whose kernel is the horizontal distribution. Recall that HM is the real part of the CR bundle. Okay, so this is the canonical distribution that comes from the embedding of the boundary in the complex space. You may choose a one form theta whose kernel is HM. Okay. Sometimes this is called in the literature a pseudo-Hermitian structure on the CR manifold, which is the boundary of the domain. And then you choose what would be called the, well, in the case of strongly pseudoconvex domain, there is a canonical choice for a vector field T with the property that theta of T is identically equal to 1. This is the Rib vector field, but in general, there is no canonical choice. So, but certainly you may choose, since the boundary is orientable, you can in fact choose a global real vector field such that theta of T is identically equal to 1. Okay, given such a pair, theta T, you define a D'Angelo form. There are many D'Angelo forms, one for each choice. A D'Angelo form alpha theta T is nothing but minus the Lie derivative along the direction T of theta. What this means is that theta is essentially a one form defining your CR structure, and T is a transversal vector field, as you see from here, right? Because to be in the kernel of theta, it means to be in the horizontal bundle. So T is transversal to the horizontal bundle, and what you are doing is you are differentiating this one form in the transversal direction. This is again a real one form, and we denote by A, capital A of M, the D'Angelo class, defined as the set of all D'Angelo forms. As you see, there are many choices here possible. For any choice of theta, again, and any choice of T, I have a D'Angelo form, and they all form a class. I'm using the word class to remind of cohomology classes, and in a moment you will understand why. But if you want to think more concretely, for any possible defining function R of your domain, you may in fact define one of these classes. How do you do that? Well, if you have R, you can consider the DC of R. I recall that the DC is I d bar minus ID of R. Well, sorry, when I say D, I mean del bar, I del bar minus I del of R. And this gives you actually gives you all possible choices as you vary the defining function of this contact forms theta. And then you choose the vector field like this, where n is a 1,0 vector which is transversal, defined to have to be such that nr is constantly equal to 1/2. With this choice of alpha and theta, you define a form for any defining function R. This will become useful later. And now the key result, the key basic result in this theory of D'Angelo forms comes from a paper of Boss and Straube. Something was already contained in the paper where D'Angelo introduced this form, but actually made a quite limited use of it. And these are the main basic properties of the D'Angelo forms. First of all, when you take one of these D'Angelo forms, alpha theta of T, its restriction to the Levi null distribution is independent of the choice of T. So, okay, since we are going only to be interested on the action of these one forms on the Levi null distribution, then T will be actually an irrelevant variable. So for any choice of theta, we will have a one form. Okay. Second important property is that if you look at the class of all, as I said, beta D'Angelo forms in the D'Angelo class, and you only look at the restriction to n, then actually this is given the same as considering one fixed beta 0 element beta 0 in the class of D'Angelo forms and adding all possible exact differentials of global smooth functions. Okay, and sorry, here I see that I put smooth function with complex values, but of course I need to be smooth functions with real values. I'm really sorry. Okay, and so the thing starts to resemble a cohomology class. What is lacking until now is closure, the closure condition. And here it comes. It's a closure condition only when you look at vectors in the Levi null distribution. So remember, beta is a one form globally defined on your boundary, and the differential of beta is 0 only when you evaluate these two forms on two vectors x and y that are both in the Levi null distribution. Okay, here I could have put the real Levi null distribution, the real part of this. It's the same, of course, because beta and d beta are real forms and so can be extended to act on complex vectors. Okay, so this is the closure condition we're looking for. This means that somehow it's legitimate to think of this as a sort of, at least, cohomology class on our boundary. And moreover, this becomes a genuine cohomology class whenever you have inside your boundary a submanifold Y with the property that its tangent bundle is contained in the Levi null distribution. In fact, more generally, whenever you have a function f, which is a smooth from any manifold Y to M with the property that its differential maps the tangent bundle inside the real Levi null distribution, then you can pull back your class your D'Angelo class, meaning you put back every element of the D'Angelo class, and you get closed forms, and they generate a cohomology class in the first rank cohomology of Y. Okay, this in particular applies whenever Y is a complex submanifold. In this case, it's automatic. This condition is automatic. The tangent boundary is contained in the Levi null distribution. Okay, so here is the D'Angelo class, and the second character I want to talk about is the Diderik-Forness index. The Diderik-Forness index is defined in the following way. It is well, first of all, you define the Diderik-Forness exponent. What a Diderik-Forness exponent is any positive real numbers less or equal than 1 with the property that there exists a defining function R for which minus r to the delta is plurisubharmonic on your domain. Okay, so you should think of your domain. Your domain has many possible smooth defining functions, and we are looking for defining function with a special property that when you raise them basically to the power delta, then you get a plurisubharmonic function. R is the defining function, doesn't need to be plurisubharmonic, not even on the boundary, because pseudoconvexity is non-negativity of del bar of R only in the special direction of the T10 of the CR bundle. Here we are requiring that inside the domain, the function is plurisubharmonic everywhere. And this is somehow a strengthening of the well-known property of a smooth pseudoconvex domains that minus the logarithm of minus R, where R is in this case, the distance to the boundary, the Euclidean distance to the boundary, is plurisubharmonic. In fact, so this is a stronger property. You don't need to take log. You can even take a positive power, maybe not 1, but a positive power. And the existence, in fact, of Diderik-Forness exponents for any possible domain is in itself a deep result established in 1977 by Diderik and Forness. Okay, so the deep fact here is that for any smooth pseudoconvex domain with no assumption whatsoever, you may always find a positive number delta with the property that minus r to the delta is plurisubharmonic. Okay, one reason why this is really interesting for us is the following deep theorem of Kohn from 1999. And this is a rephrasing of the theorem in terms of D'Angelo forms, but it's really just recognizing that some object in the statement is a D'Angelo form. So let me spell it for you. So we have a smooth bounded pseudoconvex domain as always, and the theorem says that there are constants C1 and C2 such that the following holds. Whenever delta is a Diderik-Forness exponent associated to a defining function R, so recall that a Diderik-Forness exponent comes with a defining function, then the Bergman projection on the domain omega preserves the Sobolev space HS for any S that satisfies this complicated, admittedly, inequality. But so first of all, let me recall that Bergman projection is the orthogonal projection of L2 of omega onto the closed subspace of holomorphic functions, a crucial object in many problems in several complex variables. And here what we are saying is, what the Kohn is saying is that this operator, which is a priori bounded on L2, is also bounded on HS for S positive, but not too large, or at least where S is allowed to be as large as this inequality permits. So let's look at this inequality. This inequality has 3 terms. Here there is an absolute constant C2 on the right-hand side. On the left-hand side, you have the product of 3 terms. The first is the exponential of C1S. So if you want to make S as large as possible, you better want to be allowed to make this number very large. So you want the product of the other 2 terms to be arbitrarily small. And the product of these 2 terms is 1 minus delta, 1 minus the Diderik-Forness exponent. And the other is a power of 1 plus a del infinity norm of the D'Angelo form associated to the defining function R. So here, delta and R are related because delta is this the positive exponent with the property that minus r to the delta is plurisubharmonic. Okay, so if you want to make this number small, you want to have a Diderik-Forness exponent as close as possible to 1, but at the same time, you want to keep the D'Angelo form bounded in L infinity norm, because if this goes to 0, but this is allowed to be unbounded, then you cannot be sure that S may be allowed to go to infinity. So this quite complicated statement suggests a definition for the Diderik-Forness index. So usually the Didrik-Forness index of a domain is defined as the supremum, the best possible delta in a sense that you can take for a given domain. So you look at all the possible Didrik-Forness exponents and you take the supremum of these numbers. But if you do that, then the theorem by Kohn doesn't tell you much, because of course knowing that this supremum is equal to 1 do not guarantee that S is allowed to be as large as one likes. And so to have boundedness in every possible Sobolev class. So we're going to define a regularized version of the Didrik-Forness index where the supremum is only on those delta that are Didrik-Forness exponents corresponding to the defining function whose D'Angelo form is bounded in L infinity norm by some constant k. Okay, so the definition is quite involved, but it's a natural one for this statement. If you are able to make the Didrik-Forness index, regularized Didrik-Forness index equal to 1, here k plays no essential role. If you are able to find a large constant k with the property that the Didrik-Forness index regularized, the regularized dfk index of omega is equal to 1, then delta is allowed to go to 1, but at the same time the norm stays bounded. And so Kohn's theorem allows you to take S as large as you like. Why is this so interesting? Because when the Bergman projection preserves any Sobolev class, then automatically it preserves the space of smooth functions up to the closure. And this condition is well known via some work, important work from the 80s of Bell and Ligochka, to imply smooth extensions of bilomorphisms from domains in this class. So this is really an important consequence that would be derived from the information that the Didrik-Forness index, the regularized Didrik-Forness index, is equal to 1. So again, let me stress again that if you define the Didrik-Forness index just as the supremum over all the possible deltas, such that for some defining function minus r to the delta is plurisubharmonic, then you are not allowed to conclude from the information that this index is equal to 1 that for example, bilomorphisms, smooth bilomorphisms, from two such domains extend smoothly to the boundary. But Kohn's theorem tells you that if you refine the definition of the Didrik-Forness index, as we propose to do, then we are able to also obtain this very important consequence. So let's work with this more sophisticated notion. And let's come, so now I define the Didrik-Forness index, and I define the D'Angelo class of the boundary, actually, of a smooth pseudoconvex domain. And let's see how the two objects are related. This relation emerged from work from the last year of Bingview and Liu. There are two papers in Advances in Mathematics where he found a rather complicated characterization of the Didrik-Forness index, so the simplest version with no regularization. This would be the case corresponding to k equal to infinity, as you see here. If you impose no restriction on the D'Angelo form of the defining function, then you get what is usually called the Didrik-Forness index. And he was able to characterize this number in terms of a very complicated looking partial differential inequality on the boundary. But still, this was enough for him to derive several interesting consequences. So this is an interesting paper, I think, two papers actually. And then what happened is that later, few people, I should say, including me and Samuele, started realizing that his partial differential inequality could be rephrased in terms of D'Angelo forms. And so Hume first, and then Hume and Adachi, in particular, they have a preprint from March, they gave an invariant reformulation of Liu's results in terms of a notion of Didrik-Forness index of the boundary. I'm going to even slightly rephrase the result, and let me tell you what it is. Okay, so first of all, on the boundary, we associated to the boundary this class of D'Angelo forms. What we are going to do is to define n, Gothic n of alpha for any possible choice of a D'Angelo form, a sort of norm. This is a non-negative quantity which you should think vaguely as a kind of norm. And this is defined as the infimum over all the possible positive numbers gamma with the property that this inequality holds. So the left-hand side is a non-negative quadratic form, alpha 1, 0, wedge alpha 0, 1. Alpha is a real one form, so the 1, 0 part and the 0, 1 part are, of course, well-defined. When you wedge them, you get an object which we think as an Hermitian form on the T10 of the boundary, but actually we're gonna only to look at it on the Levi null distribution. This is crucial. And the right-hand side is the D bar of alpha 1, 0. One shows that this object is well defined, is also an Hermitian form on the Levi null distribution, and you're looking for all possible gammas such that this inequality holds, and you take the infimum. Okay, again, this looks still quite complicated, but at least invariantly defined. And it's immediately apparent that this quantity is at least homogeneous of degree 1, in the sense that if you multiply by t, a real positive t alpha, then multiplying both sides of this inequality by t squared, you see that the n of t alpha is t of n alpha. So it starts resembling some kind of norm. And then, since your domain has associated not a single D'Angelo form, but the whole class of them, we're going to take the infimum of these norms over the whole class. So this again resembles the definition of a quotient norm. Okay. Remember that the D'Angelo class is an affine space of D'Angelo forms. So this is looks really like the quotient norm on a vector space. Okay, so in other words, the D'Angelo class has associated to it a positive, well, a non-negative quantity, the quantity that I denoted as Gothic n of n. Okay, now what is Adachi-Hume result, which again is, as I said, it's an invariant reformulation of a result of Liu, which at least it was originally stated in Cn, and then of course the invariant reformulation allows you to state it in more general manifolds, but let's think of Cn, it's enough for us. And the theorem is quite simple looking now that we have all the definitions. The Dideric-Fornès index of omega is just 1 over 1 plus this norm-like object, n of m. So again, if you remember that n of m may go from infinity, then you see that the Dideric-Fornès index varies between 0 and 1, and more importantly, that the Dideric-Fornès index is 1 if and only if this quantity n of m is equal to 0. So this is what one has to look for. And remember that we're really interested in the regularized version, so we're just going to regularize everything, and the norm nk will be not the infimum over all possible elements in the D'Angelo class, but only on those of bounded norms. And if you do that, then you have the corresponding result. This is just really a matter of carefully checking constants in the proofs, and this works. Okay. So what are the consequences of this result? As I said, let me go back a second. The Dideric-Fornès index will be 1, which is an exciting consequence for us when nk of m is equal to 0. So this is what we're going to look for. Well, first of all, here I recall that Liu already used this more complicated non-invariant formulation to determine exactly the Dideric-Fornès index of worm domains. Remember that worm domains contain an annulus on their boundary, and A and B are the parameters defining the two radii of the annulus. Some B over A is just the parameterizing all the possible complex structures on an annulus, and this is the parameter that determines completely the Dideric-Fornès index of the domain. And as you see, this index is never 1. It's always strictly less than 1. And it's worth saying that this is actually the first and unique to date example of a Dideric-Fornès index which is explicitly calculated. As we'll see, as a consequence of our results, we'll know that many domains have Dideric-Fornès index strictly less than 1. But these are the only class of domains which have Dideric-Fornès index strictly less than 1, which is actually known, and it's equal to 1 over 1 plus 2 over pi log b over a. So this little number b 2 over pi log of b over a is actually the norm n that appears here. Okay, this is already pretty interesting. And okay, so in the process of actually in parallel to Hume and Adachi, I'll reshaping Liu's result in this invariant fashion. Our first goal was, okay, let's try to find the class of domains for which we know that this norm is positive, nkm, and so we can conclude that the Dideric-Fornès index is strictly less than 1. And here is our first result. And the result just says that whenever you have a complex manifold in the boundary such that the pullback of the D'Angelo class is non-trivial as an element of the rank homology of your manifold Y, then the Dideric-Fornès index is strictly less than 1. So remember that A of M is the D'Angelo class when you pull back along a holomorphic mapping, such as the inclusion of a complex manifolds in the boundary, then you get a cohomology class. So this cohomology class was the cohomology class parameterized by the pluriharmonic function in the case of complex hypersurfaces in the boundary that I described earlier, or the real valued harmonic functions on Riemann surfaces that I described when I showed you the picture of domains containing Riemann surfaces in their boundary. So whenever this happens, then automatically the Diderik-Forness index is strictly less than 1. Okay, this is a qualitative result. It has a quantitative counterpart, but let me first sketch a geometric proof of this fact, which is actually quite simple. Well, first of all, whenever you have a closed one form on your manifold Y, you may use exactly the same definition as the Gothican norm defined in the previous slide to introduce again a norm-like object on closed one forms. And this descends to cohomology by taking the infimum over all the representatives closed one forms of a cohomology class. And what one sees is that if you have two complex manifolds, so the object I just defined is defined on closed one forms and then cohomology classes on a generic complex manifold. And what one verifies very easily is that when you have a holomorphic mapping between two complex manifolds, then the pullback, which induces, of course, a mapping from the H1 of Y to the H1 of Y0, in terms of this norm, which I'm calling a norm, but I didn't prove it until now, actually, is this norm-like object is decreasing. So this is, well, sorry, increasing. The norm of the pullback on Y0 of a form alpha on Y is less or equal than the norm of the form alpha. What this means is that if I want to show that the norm, Gothic norm Y of alpha is positive, which in terms, thanks to the theorem, let me show it again, is what I need to see to conclude that the Diderik-Forness index of omega is strictly less than 1, then what I want to prove is that there is at least a complex manifold Y0 and a holomorphic mapping with the property that this quantity is positive. And this, if one thinks about it, boils down, and it's a consequence of the fact that embedded complex annuli generate the homology of any complex manifold like this. So essentially, the Y is a manifold, a real analytic manifold in particular, and one knows that the loops representative of homology classes may be chosen to be real analytic, and then by an analytic continuation argument, one finds actually embedded annuli, holomorphic annuli, inside the manifold with the property that they generate the homology. And as a consequence of that, this norm may be shown to be positive. And so the theorem actually, in some sense, reduces to the known cases of worms, where we actually know that the Diderik-Forness is strictly less than 1, and these norms are positive. So this is just a sketch of a geometric proof. Let me show you instead an analytic proof of the same statement. In the simpler situation where Y, which was the complex manifold, is in the boundary, is in fact a pseudoconvex domain itself inside Cn. Okay, let me just briefly sketch it. So, as I said earlier, since Y is Stein, cohomology classes are represented by pluriharmonic functions H. So now I want to prove that the Diderik-Forness index is strictly larger than, it's strictly less than 1. So I will argue by contradiction and assume that the Diderik-Forness index is 1, or actually in a quantitative way, assuming that the Diderik-Forness index is larger or equal than 1 over 1 plus epsilon. And let's see what's the consequence. Then, unraveling the definitions, what we have is this inequality. Remember that thanks to the theorem, Diderik-Forness is related to this norm. So to say that the norm is positive means exactly that. The norm is small, sorry, is epsilon. It means exactly that, where H is a pluriharmonic function and F is some smooth function. So this is a starting inequality we have to begin with. And then what we do is we trace the inequality. One can then integrate against tensor function to a quite standard argument in PDEs, use Poincare inequality, and what one eventually finds is this remarkable inequality. This is telling you that on every ball contained in the domain, the average of F minus its average, so FB is just the average on a ball, is bounded by this quantity. So this is the well-known BMO condition. And then one can invoke John Nirenberg inequality to conclude that our function F, which remember, is just defined as some smooth function satisfying this inequality between actually quadratic forms, this differential form inequality, satisfies this exponential integrability condition. So forget about the constant. This is just telling us that the integral of the exponential of f is finite. So this is a very strong integrability condition. And okay, and then this condition is really good for us because we can use our Mandel-L2 theorem to solve the d-bar problem with datum d-bar h minus if. Of course, this 0-1 form is d-bar closed, and so I can solve the d-bar problem with a smooth function u. This condition, actually, and let me go back, the first inequality on quadratic form is exactly the hypothesis of one of the formulation of the Allmander solvability theorem for the d-bar equation. So the consequence is that I can find a smooth function u such that this holds. d-bar of u is equal to d-bar of h minus if, but this just means that u and h minus if differ by holomorphic function. And in particular, taking real parts, I discovered that h, you see that if is purely imaginary, then h is equal to u plus the real part of a holomorphic function. And of course, Allmander theorem comes with a bound, but the bound involves the integral of the weight of the e to the minus phi. But thanks to our John-Nirenberg argument, given exponential integrability, we can use Cauchy-Schwarz and just bound the L1 norm of u. So the conclusion, to put it simply, is that we are able to control the L1 norm of u, and u, as you see from the first highlighted inequality, is nothing but the difference between our pluriharmonic function h and the real part of a holomorphic function. So you see that if epsilon is very small, then this L1 norm goes to 0, and actually the pluriharmonic function is the real part of the holomorphic function, and this means that cohomologically it is trivial. Okay, so this is just the second sketch of the analytic proof. I wanted to show it because it's quite interesting. There are two so different arguments to establish essentially the same result. The advantage of the analytic proof, well, the difficulty is that it's more difficult to make it work on more general manifolds. There are several technicalities, but the constants that come with it are explicit, and it allows us to get quantitative bounds out of it. Okay, but let me not dwell on it. It's already a bit late. Let me see, how much time do I have? I didn't check what time did I start.
Okay, 2 minutes, but you can take some minutes more.
Sorry?
Okay, 2 minutes.
Ah, okay. So
but you can take some minutes more. That's
okay. I will try to 4 minutes, let's say, so I'm able to discuss of the last topic. Okay, what I want to talk about now is a final improvement over this theorem. Let me go back to Adachi and Hume theorem relating the Diderich-Forness index and this norm nk of m. Okay, what is this improvement? This improvement involves a stratification of the boundary of a smooth pseudoconvex domain. Okay, first of all, to define it, let me recall this notion of tangent bundle for an arbitrary subset, closed subset, let's say, of a manifold. When you have S, a subset of a manifold M, then one is able to define its somehow tangent distribution, I should say. It's not really a vector bundle, where a vector is said to be tangent to, I'm sorry, this capital F should be S. So the vector is tangent to S if and only if it kills every smooth function that vanishes on F, that vanishes on S. Sorry. So this is the smooth analog of the definition of the Zariski tangent space in algebraic geometry. So it's a quite natural notion, and it allows you to talk about of the tangent bundle or distribution to an arbitrary compact set, which is what we need because we're going to apply it to the set of weakly pseudoconvex boundary points that have no geometric structure in general. They're not a smooth submanifold. Okay, and these are the two key operations I want to talk about to define to state the final theorem. Okay, whenever one has here it's written again a bundle, but what I really mean is a distribution. So for every point of my manifold, I'm assigning a subspace, a complex subspace of the complexified tangent bundle. You should think of L as the Levi-null distribution. Later, I will apply this consideration to the Levi-null distributions. Then I have two possible operations. I can look at the support of these distributions, which means the set of points of the boundary where the distribution is non-trivial. And then I have an operation of reduction, which is slightly more complicated, but actually very natural. What we are doing is we are looking at our distribution and intersecting it with the tangent to the support of the distribution. Okay, in a moment I'll give you a picture to try to explain what this means, but essentially if you have a vector, if you have a vector distribution of subspaces, then you only want to look at vectors in this distribution that are also tangent to the support of the distribution itself. At any rate, this is an operation that, given a distribution L, associate to it a smaller distribution rad of L. And it's crucial to realize, in fact, that the support of the new distribution may be much more smaller, because in fact I'm removing all points where the distribution is transversal to the support of the distribution itself. So, and then one may iterate this procedure. This looks very complicated, so let me try to look to give a simple example of a real analog. I'm not going to draw complex distributions. So here the manifold is the complex plane, and in red I described a distribution. So for any point of the complex plane outside the union of the two axes, I'm looking at the figure on the left now. For any point outside of the axis, the distribution is trivial. So the subspace is just a zero subspace. For every point on the vertical axis and on the horizontal axis, I have in my distribution the horizontal subspace, so generated, if you want, by the vector d over dx. And then only at the origin, you see, the rank of the distribution is 2. Okay, this distribution is has the semi-continuity property of Levi-null distribution, so this discontinuity is somehow allowed in our framework. So what happens when I do the reduction? What I have to do is I have to look at the intersection of my distribution with the tangent to the support of the distribution. What is the tangent of the support of the distribution? It's just the union of the coordinate axes. And what is the Zariski, smooth Zariski tangent to this set? Well, since it is smooth outside of the origin, this is just the ordinary tangent. But at the origin, I have the full two-dimensional subspace, R2. So when I intersect my distribution with the tangent, well, the whole vertical line except the origin disappears, because here the distribution is transversal to the support. But this is what survives. At the origin, the full rank 2 subspace, tangent space survives. Dimension 2 dimension 2 tangent space survives, and outside of the origin I have what I had before, because the distribution is tangent to the support. Okay, and this to show that in this case, this is probably the simplest example where you need to take another operation of reduction, and you can still simplify somehow your distribution, because now the tangent to your support, which is only the horizontal axis, is allows you to remove the vertical directions from the distribution of the origin. So the resulting distribution is just the dx distribution, horizontal distribution on the horizontal line. So this is an example when you take 2 steps. And so what is our final result? Well, we're going to apply this procedure, as I said here, well, to not to a generic distribution n, but to the Levi-null distribution n. Okay, and I'm going to define the norm exactly in the same way, but in a possibly much smaller distribution. So since the condition is required on a smaller distribution, this infimum is in general larger a priori. And then I have a version with the regularization. Let's not worry about that. And this is our theorem, that actually you may replace the norm. So typographically is a tiny variation on the previous result. We are allowed to not to add this blue L here, and to take the norm in this much smaller null subspace. So this means that, in fact, if you want to prove that the Dideric-Forness index is equal to 1, it's enough to prove that NL is equal to 0. And this is easier to show than to show when L is larger, let's say. So in particular, if you're able to find a large L for which this NLM is equal to 0, then you may guarantee that the Dideric-Forness index is 1, and the Bergman projection preserves the space of smooth functions up to the closure, and all the consequences related to Belli-Gochka theorem. And this is really the last slide. I wanted just to give examples of when we can actually use this theorem to prove new results. So one class is the weakly regular domains. Whenever a domain is weakly regular, we can show that actually the stratification allows to conclude that the support of the iterated reduced distribution eventually becomes empty. And this means that if the set is empty, there is nothing to check. And so the infimum here, the norm, sorry, is 0. Okay. And if the norm is 0, the Dideric-Fornés index is 1. So this generalizes results of Liu and also of Krantz, Liu, and Peloso, where they showed that the Dideric-Fornés index is 1 whenever the set of weakly pseudoconvex points is a real curve in the boundary. Here is more general. You may allow actually any weakly regular domain. And finally, you may even not get to the empty set in your stratification, but get stuck to a set Sn with the property of essentially having a tangent which is included in the Levi-null distribution and, for example, trivial H1 group. In this case, also, we are able to conclude that the Dideric-Fornés index is equal to 1, and this is related to results of Boss and Straube from 2008. Okay, since I guess I'm late, I apologize, and I thank you for your attention.
Good. Thank you. So, other questions, remarks?
Should share again.
So, Gian Maria, just curiosity, I don't think that there is a positive answer, but just to know, is there any relation between the Dideric-Fornés index and the squeezing radius of a domain?
I'm sorry, I don't know about that. I've seen a few papers about this, but I'm not sure. Nothing meaningful to say.
Okay.
There is a question by Fausto.
Oh, yes, thank you. I would like to know whether, if you know an elementary proof of the fact that if you have a D'Angelo finite type pseudoconvex domain, then almost every point in the boundary is strongly pseudoconvex, which does not use Catlin's results. And I think there should be an elementary proof, but if you know of it, one sub, or well, that's the question.
I also thought about similar questions. It's true that these relations between because the notion of weak regularity may be used in maybe not elementary, but not as messy and complicated as Catlin's arguments are to prove consequences of it. But somehow the problem is that whenever you want to prove that a domain is weakly regular starting from finite type, the more understandable arguments that I know are arguments of Sibony, where he proves actually that weak regularity is implied by some finite type condition. But I think in his paper in Duke from 1987 probably, where he introduces the notion of B-regularity, in particular he proves that finite type implies weakly regular in a not so complicated way, and that would of course imply what you say. The problem, I guess, is that the argument as it's written, it's not precise, and it's actually valid proof if your notion of finite type is what's called Bloom finite type. So there are a few notions of finite type. So if you are referring to D'Angelo finite types, so bounded order of contact with complex curves, so my answer probably, I could have said immediately, is sorry, I don't know, I don't have a simpler argument. There could be one. But if you allow other notions of finite type, for example, these notions involving iterated commutators of vector fields, then I think in the paper of Sibony there is a decently readable argument to prove that. I don't know if that answers.
Thank you.
Marco, did you raise your hand?
Yes.
Yes.
I apologize, I arrived late. Maybe you said already. So did you discuss the non-trivial Neberhunden for these domains? Did you prove them?
No, I mean, I didn't talk about this. So what's the precise question?
Well, if you take a pseudoconvex domains that contains strictly the closure of the domain, this is strictly larger,
Yes.
as in the case of the classical worm.
Yes. So you want to know if these more general domains also have
So,
the property that they have non-trivial.
non-trivial.
But this,
Yeah.
okay, there is, I hope I'm not quoting it wrong, but in the case of complex manifolds in the boundary, there is a result by, okay, I hope it's bad for M4ness, where they actually relate another norm on cohomology. So as I said, the moral is that whenever you have a complex manifold in the boundary, you got the cohomology class. This cohomology class may be used to compute the Diderot-Forness index in terms of an appropriate notion of norm, which I discussed. And this is related to my result with Samuele and previous results of Adachi and Hume. There are other notions of norms on cohomology, and there is one which is related to the problem of non-trivial Nebenbulle. So I can if you didn't understand which paper I'm talking about, I can send it to you.
Yeah. Okay.
Because okay, I don't remember the journal or the exact year, but.
And the other question that I have is whether you thought about whether the Dietrich-Fornett index is the biolomorphic invariant or not. To the best of my knowledge, is still an open question.
I agree. I think anything that, I mean, whenever you define an invariant in terms of the, okay, the Dietrich-Forness is somehow defined in terms of the boundary, and actually this kind of theorems shows you that it's equivalent to some quantity attached only to the CR structure of the boundary. And whenever you define something in terms of the boundary, and you don't know that biolomorphisms extend smoothly, somehow you got a problem, because it's quite circular. If you want to show that it's biolomorphic invariant, you need to know that you have smooth extensions of biolomorphisms, but somehow you use these results and these techniques to prove instances of the conjecture of smooth extendability of biolomorphisms. So again, I guess this is all of this, by the way, behind all of this is the fact that you may be able to prove for larger and larger classes of domains that you have smooth extendability to the boundary, but Christ's result from 1996 telling that you don't have this smooth, this preservation of smooth functions up to the boundary by the Bergman projection tells you that this approach is doomed to failure for general smooth pseudoconvex domain. On the other hand, I'm not aware of any other approach that is able to establish smooth extendability for so general domains. There are, of course, more geometric approaches that are more informative in other terms. Again, Filippo talked about this. But if you want to deal with general smooth pseudoconvex domains,
yeah,
no idea.
Okay.
Okay. Are there other questions? Let me check the chat. I saw one hand. Fausto.
Era ancora Fausto, sì.
Oh, okay. It was okay. It was okay. So if there are no other questions, well, let's thank Gian Maria again. So as Filippo said, we'll resume next week.
Yes, there will be Luca Baracco.
Oh, Luca Baracco.